let's start with our new topic, the discovery of electron. So I'll give you a brief detail or a background behind the discovery. So in the late 1800s, what was happening that almost every scientist was performing a experiment known as glass discharge tube experiment. And out of a blue, there came a scientist, J.J. Thomson, and he claimed that he has discovered a new particle other than atom, right? Because till then everyone was thinking John Dalton is correct and atom is the fundamental particle. But when he said that no, there is another particle which is in the existence, and he named it as electron, and we'll study the same thing in this discovery of electron. How does the experimental setup was, what were the observations, and how did J.J. Thomson reach that conclusion, the new particle known as electron. So let's start with it. I'll give you a detail about the experimental setup. This is how the experimental setup was look like. So there is a glass discharge tube which is blue in color right now, and in that we have fitted a cathode, a anode, and the pressure inside the gas was kept very low. We'll study why was that, why we kept the pressure low. Also we had a vacuum pump and a very high voltage generator. This has almost a voltage of our 10,000 electron volt, and these were the cathode rays. So we observed that the cathode rays were moving from the cathode to anode, and that is why we call them as the cathode rays, because they were traveling from the cathode to anode like this. So this was the very simple experimental setup. Now we'll study what were the experimental setups in more detail. So let's see. So the first thing was the pressure inside the gas was very low. It was because so that the particles of gas do not collide with each other, right? You just saw that the particles are moving from cathode to anode, and we call them cathode rays. We haven't named them as electrons now. So that these particles do not collide with each other, the pressure of the gas was kept very low. The next setup or condition was, you can say, the anode was porous. Why the anode was porous? So that the particles of your cathode rays can travel from anode to the behind of the screen, and at the behind we had a fluorescent material which was zinc sulfide, and zinc sulfide, whenever it strikes with an electron or some another charged particle or a subatomic particle, it glows in the dark. So that is why this was present behind the anode, or you can say the screen was of zinc sulfide. So the last condition or your setup was that the pressure inside gas was low, and why it was I have already told you, so that the particles do not collide with each other. Now we'll see what were the observations we saw during the cathode ray experiment. So let's see the first observation of the cathode ray experiment. The first one was that cathode rays were traveling in a straight path from cathode to anode. Why they are called as cathode rays? Cathode rays you have understood, because they are traveling from cathode, they are originating from cathode and ending to anode. So they were traveling in a straight line. We'll study that how did we reach this idea that they are traveling in a straight line. Then the next observation was they were deflected in both electric field as well as magnetic field. This fact told us that the cathode rays might be having some charge. We do not know yet what is the charge. We cannot assume it, right? At that time they never knew that they are discovering electron. So they just concluded that they might be having a charge. The next observation was that cathode rays were producing fluorescence. Why? Because on the screen, if you remember, there is zinc sulfide material, or the screen is of zinc sulfide. Whenever the electrons were colliding with zinc sulfide screen, they were producing fluorescence. The next observation was they were producing the X-rays. I guess all of you are familiar with X-rays, that doctor use it to find a fracture in the bone. The another observation of the cathode ray experiment was that it is a very important one. This will tell you that electron is a fundamental particle. So see, what was the observation? That firstly they changed the cathode. Let's say they took a gas of helium and they were using, let's say, carbon electrodes. Then they used the same gas, helium, but they changed the type of electrode. Let's say they use platinum. What they were observing was that the characteristics, we'll study what characteristics we are going to talk about. The characteristics of the cathode rays was not changing. Then what they did, they tried to change the gas. Let's say from helium we took neon now. Even taking neon or any another gas, the characteristic of your cathode rays was not changing. Let's see the next observation. The next observation was that particles which are making the cathode rays are basically the fundamental particle. Why? We just saw in the previous observation is that on changing gas or electrode, the characteristics are not changing. So that is why the scientists, or you can say the J.J. Thomson, reached to a conclusion that might be cathode rays are made up of fundamental particles. Now let's see the next observation. The next observation, or you can say what J.J. Thomson did, he tried to find a charge to mass ratio of the cathode rays. So he was successful in it and he found that charge to mass ratio was found to be 1.75 into 10 to the power 11 coulomb per kilogram. He found the same value even on changing the electrode, changing on the gas. So that is why we are saying that the cathode rays are fundamental particles. Why I am pinpointing this thing out? Because we're going to talk about the proton and neutrons later, and we'll study that they were not fundamental particles. So this value, when he calculated, then there was another scientist who was working on the charge of electron. So there was a scientist Millikan, he found the charge on electron was 1.6 into 10 to the power negative 19 coulomb using the very famous oil drop experiment. So from there, when we saw E by M ratio is 1.75 into 10 to the power 11 coulomb per kg, correct? And your charge is 1.6 into 10 to the power negative 19 coulomb. We can find the mass of electron from here. How? So see, we cannot use some conventional weighing machine to find the mass of an electron because they are subatomic particles, so we cannot find their mass. So how do we find them? We find them by these alternative methods. So from here we can find the mass of an electron. It is equals to 1.6 into 10 to the power negative 19 coulomb divided by 1.75 into 10 to the power 11 coulomb per kg. And on solving this, you will get the mass of electron to be 9.11 into 10 to the power negative 31 kilogram. So these were the observation of cathode ray experiment. Now we will move to the conclusions of cathode ray experiment. So let's see the conclusion and the explanation behind the observations. The very first observation